All right, in this option, we're going to look at describing the free radical mechanism involved in the production of low-density polyethylene. So this is a type of plastic. If you turn over a piece of plastic that's recyclable and you look at the label, underneath these sort of triangular, circular arrows, you'll see LDPE. And there's also high density. So in C.9.2, we're looking at the Ziegler-Natta Catalyst in the manufacture of high-density polyethylene, and that's usually denoted by HDPE when you look at the label. So let's take a look at what they actually look like structurally. So LDPE, the low density, what you end up with is a sort of chain with lots and lots of branches, and those branches are important because it means that these layers can't get close to each other, and when there's increased distance, that means there's decreased attraction. And in this case, because it's all organic molecules, we're going to be thinking about van der Waals. When we look at HDPE, actually each layer becomes very, very tightly sort of fitted together with the layer before it. So because they're very close together, they have high van der Waals. So we have low density due to branching and high density due to no branching, perfect layers. And we're going to look at how those are produced and why that is. The branching will result in the weaker van der Waal. The important part to note then is that it will have a lower melting point, whereas the strong van der Waals will give HDPE the higher melting point. Now the manufacturing conditions for these two differ. LDPE happens at a higher temperature and pressure, whereas HDPE happens at a fairly low pressure and a lower temperature. So now let's just focus first on the LDPE. Now this is a free radical mechanism. So with all free radical mechanisms, we have an initiation phase. So there's a new group which is not part of the core called a peroxide functional group, and that's basically two oxygens together. So this one here with a single bond between the two, that's a peroxide group. So what you start with is a peroxide, and it's going to form a free radical to the high heat or temperature that we showed on the previous page. So when that happens, it splits apart. This bond between the two oxygens is relatively weak, and so it has the lowest bond enthalpy. It separates. So what we have here then is an oxygen that has one electron. Of course, it wants to get one more to complete its octet. Now that we have the radical, we always have the propagation phase. So what we're going to do is we're going to take this radical, free radical, and we're going to react it with ethene, because we want to make a polymer of ethene. So we're going to bring in an ethene molecule, and then we're just going to rewrite this one more simply. So R in this case is just going to represent everything over here, and then we'll just put the O with the electron. So when these react, what happens is the electron from the double bond is going to try and go over to fill this oxygen's energy levels. So you can see that when that happens, it now has joined, and we have a new bond here, but there's still one electron left over. Of course, one went over here to satisfy, but there were two in this bond, so one stays over here, and so we still have a free radical, so we have propagation. Now it's going to continue on. When this one encounters another ethene, then the same process is going to happen. One electron is going to go here, and one's going to go here, and then you're going to end up again with a longer chain with a radical, and if it encounters another one, it will continue and continue. Now with all our free radical mechanisms, there can be a termination phase, and so what you could sort of think about is just taking any one of these and then encountering another one of these. So like two of these where each of them would have one electron, they would form a bond there, and then that would terminate. You could also do that with this one. So for the HDPE production, we're going to be using a catalyst called the Ziegler-Natta Catalyst, and that one it has a crazy mechanism, an ionic mechanism. And basically you don't need to know the details of that, and that's a good thing because it's quite involved. But basically you do need to be able to identify what a Ziegler-Natta catalyst is made of. And so what it actually is it is titanium with 4 chlorines, and these chlorines and titanium, the bond is actually more covalent than ionic, and together with an aluminum with some ethyl groups attached. And so you can sort of just look at it that way. Together, and again we're not going to look into the detail, this is a catalyst that is going to help make the HDPE. Again, polyethene, but we're just going to actually change how the branching happens, or doesn't happen in this case. So starting with an ethene here, and to simplify the diagram, the actual active site of the catalyst where this occurs is the titanium. So what will happen is in the pi bond here, the electrons will travel into titanium's empty d orbitals, and that process allows for this ethene to actually insert itself, the whole rest of it inserts itself to the end of the chain, and the titanium sort of moves to the end. And then another ethene will come along, the same thing, the electrons will go to the titanium for a moment, the rest will sort of sneak its way in between, and the titanium will move to the end. So this just keeps repeating itself, but the important part is that it creates a straight structure, whereas the other one can create branching through the free radical mechanism. This ionic mechanism creates very, very few branches. So the wording they're looking for is that titanium utilizes its empty d orbital. And if you want to try and think about how that happens, titanium, when it's with 4 chlorines here, it will have all of its d orbitals full except for this one. So there's some space for some electrons to come in and fulfill its needs. So that's essentially the outline of the production of LDPE and HDPE.